Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very fortunate to be joined by Tristan Guillot, who's come across to us. He's currently on sabbatical at UC Santa Cruz. Tristan did his bachelor's in mathematics and physics at the University of Avignon, and then a master's in physics at the University of Marseille. Before he did his PhD in internal structure of the giant planets at the University of Paris, number 7. And he did a postdoc at the University of Nice, Sophia Antipolis, where he worked on the physics of substellar objects. Tristan, in 2002, was the recipient of the bronze medal of CNRS. And in 2006, he was awarded the Zeldovich Medal of the Coast Bar and also the Urey Prize of DPS. His work revolves around several topics related to giant planets and is particularly relevant to exoplanets these days, including phase separation, dense plasmas, molecular opacities at high pressures, condensation and convection of planetary atmospheres, and also extrasolar giant planets and brown dwarfs, which we're going to hear about today in his talk. So if you'll join me in welcoming Tristan.
Okay, thanks, Adrian. Yes, it's been really a revolution in the past 15 years or so, thanks to the discovery of exoplanets, as you are all aware of. Today, I'm going to concentrate on some of the objects that are generally less talked about, which are massive giant planets and what we call brown dwarfs. So those are objects that are in between giant planets and stars. We believe they're formed as stars, but they're not massive enough to burn hydrogen and have a main sequence of hydrogen burning as the sun has. And thanks to this discovery of this population, both of low mass planets and high mass planets and brown dwarfs next to their stars, we will see that we can really learn a lot about what's happening in these systems. And in particular, I will try to convince you that some of these objects disappear along during the evolution of the systems due to tides that are exerted between the companion and the parent star. So this is a standard diagram that you've probably seen a lot in some various shapes. It simply shows the orbital distance and the masses of extrasolar planets and brown dwarfs. And you can see that there's really a huge variety of objects. I don't know what's the number of discoveries right now. It's probably around 600 or so, maybe 700. And then you have to add all the new Kepler candidates. Most of them are true planets. So we're really around the several thousands now. So it's really a very exciting time. And you can see in this diagram that we've been able to discover both low mass planets. So this is in Earth masses. So we have some objects that are down there. And probably we even know some objects that are really close to the Earth mass now. And all the way up to the stellar regime. So generally when we try to classify these objects between 1 and 10 Earth masses, we'll talk about super Earths. So something that's like the Earth, then bigger, maybe we think it should be made mostly of rocks, but then is it the case? We don't know. Then between 10 to say 30, 40 Earth masses, we have ice giants, planets similar to Uranus and Neptune. Maybe we could have very different compositions. And then higher than 30 Earth masses begins the domain of the giant planets. So those are believed to be objects that are mainly made of hydrogen and helium, although we have some surprise there concerning their composition. Some are really dense. And that goes all the way to perhaps at least 10 Jupiter masses, maybe more, we don't know. So those are objects that presumably formed in a disk around a star, like planets, and acquired a lot of hydrogen and helium. And then beyond that, but the distinction is not very clear. Does it occur at 3 Jupiter masses, 10, 15, we don't know. There's the regime of brown dwarfs. So those are objects that we believe are formed as stars, but they can be very close to their parent star. And you can see them in this diagram starting at around here. So, well, this is 3 Jupiter masses. So in this regime, this is the domain of brown dwarfs. And then above that, you have stars. And we know there are lots of binary stars, and this is also something very interesting. So there are lots of things that I could talk about in this diagram. You can see the structure and all that. And there are other things to be done for part of these objects. For example, we can now measure sizes of some of the objects because they're transiting in front of their star. So we have a lot of information, and we can really see in terms of structure that there's something going on. So we have the small mass planets that are there and that are both low mass, of course, but also small radius and quite dense generally, although it's not always the case. And we have this regime where we believe we have planets like Uranus and Neptune, so with a little bit of hydrogen and helium, ices and rocks. And then we have the regime of objects that contain a lot of hydrogen and helium. So those are the giant planets and the brown dwarfs. So we can really study them, characterize them, and it's really something. Sorry, the colors, well, in this talk is just to that it's nicer, but they do indicate something, which is the metallicity of the parent star. So some stars have a lot of heavy elements we call metals in astronomy. Some have less, and here it's mostly to show that there is a variety of objects. We can find planets and brown dwarfs around metal-poor stars and around metal-rich stars as well. So the diagram I'm going to concentrate on is mostly this one. So it's a slightly different one in the sense that I've plotted here on the y-axis the mass of the companions, although it's to be more precise, an m sin I, because there's a degeneracy with the inclination for the objects that have been discovered by the radial velocity technique. And on the x-axis, I'm putting the effective temperature of the star. So it shows us that there's also a variety of stars that have that are known to have planetary companions. So basically, we have the cool stars here, where it's quite difficult to find planets, so there hasn't been many detections. Most of the detections have been done around stars that look like the sun, So the Sun would have an effective temperature of around 5,800 K, and Jupiter would be, that's in Jupiter units, so Jupiter would be exactly here on this diagram. And then you have planets that have been discovered around stars that are hotter and more massive, so-called F-dwarfs. And in this diagram, I've played a little bit with some parameters. So again, the color is the metallicity of the star, but this is not something I'm going to talk a lot about. But most importantly, the size is related to how close the companions are, so that your eye is more attracted to companions that are very close to their star. You can see that the orbital periods range from a day or so, very close to the parent star, to 100 days and more. So we're able to detect things that are even quite far. But what in this diagram, there are lots of white places where we don't have any detections. Some of them are due just to observational biases. Like it's very difficult to observe a small planet around a big star. And those are hot stars, generally they rotate fast. So there's a strong observational bias here. There's also an observational bias there because those stars are very faint. So it's difficult to have a lot of detections. But what I'm going to focus on is this void here. You see that there's a lack of objects. And this is what I call the brown dwarf desert. It's something that has been proposed many years ago when people looking in radial velocimetry didn't find brown dwarfs close to solar-type stars, or very few of those. Brown dwarfs are observed quite commonly in young stellar clusters, but they float freely, they form like stars, they're very young, so we can still observe them. There are a lot of brown dwarfs in the universe, but close to solar-type stars, there's much less. And the new thing here, the new discovery of the past few years, thanks to transit surveys, is that although there's a lack of brown dwarfs and massive companions around stars like the Sun, when you look at stars that are slightly more massive, F-dwarfs, we find quite a bit of massive companions there. And there's no bias of detection that would favor these stars against these ones. Actually, it's more difficult both in radial velocimetry and with transit surveys to find those objects there than there. So, so this is a real trend. Let's look a little bit at the objects themselves. Of course, the most interesting ones are the ones that lie close to this border, and I'm going to focus on two special ones, which are Corot 18 and Corot 2. Corot 2 has been discovered by the Corot mission early on. This was the second planet discovered by Corot. Corot is a satellite mission led by CNES, and the satellite is on a low Earth orbit. It's like Kepler, but it cannot stare on the same field for the entire duration of the mission. So instead, because depending on the winter and the summer season, you have to switch fields, it's selecting new fields each 6 months or so. And so it's been discovering a lot of very interesting objects, especially in the giant planet regime. And we're going to talk about these two. And then there are other objects there that are also very interesting. Generally, here you have companions that orbit stars that are fast rotators. And actually, I will show in the next diagram that there's also something we can look at that's a little bit different. This is just stellar physics. This diagram shows the effective temperature of the stars with companions, so same as before, as a function of the v sin I, so the rotation speed of the stars themselves. So this has been measured by the broadening of the spectral lines, and you can see that you have the bulk of object is down there. This is a well-known effect, and I'm going to come back to that later, that stars that are hotter and more massive tend to rotate more rapidly. This has been known for many, many years. But what's interesting is our two objects that are highlighted, Coro 2 and Coro 18, they're standing out of the crowd. You see here, they have much larger spin rates than their counterparts that generally tend to be lower. So this is something really interesting. So I'm just going to show you the light curves of these two objects as measured by Coro. So this is the satellite itself. Coro 2, for Coro 2 we have a very nice light curve, so 145 days or so continuously. It was a real surprise to discover this object. So what you can see here is the variation of the stellar flux due to spots on the star. So it's a very active star. It's rotating rapidly, so the light curve seems very noisy, but this is not noise. This is just spots on the surface of the star. And then you have these lines there, and those correspond to the transits of the planet itself. So the star is orbited by a planet that transits every 1.7 days around it. So this is something that would have been very hard to discover from the ground because the light curve is so noisy. Coro 18 has been observed for less time, so about 20 or 30 days. So this is a blow-up. It seems like a blow-up of this light curve, but it's not. It's really another target. And it looks very similar. So you have, again, a quite seemingly noisy light curve, also due to spots on the star. The star is rotating very rapidly, and then you can see the transits of the planet in front of it. So the incredible thing about these objects is that they are very similar. They are almost twins. So we have, for Coro 2, a planet which is around 3 Jupiter masses. It's very inflated, oversized, 1.5 Jupiter radii. It's really huge for its mass. So it's a planet that we really can't explain with standard models. We need something dramatic that happened recently, like a giant impact, or maybe there's something we don't understand there. So the planet is orbiting the star every 1.73 days. The star has a 4.5 day spin, and so it looks a little bit like the sun. It's a little bit less massive, solar metallicity. Coro 18, as you can see, looks almost identical. The planet is a little bit smaller, but it's the same mass basically. It's orbiting on a 1.9 day period. The star is a little bit slower, so 5.4 days, but basically it's also something that's very similar to the sun. So when you study this system, they have to be very young. Both of them, Coro 2 has been observed in X-rays, and it's probably around 100 to 300 million years. And Coro 18 is probably a little bit older, but it's still a very young star. Although for Coro 18, I mean, for Coro 2, we have a problem with the size of the planet that we can't explain. For Coro 18, we have actually a problem with the age of the star, because different methods give different ages. So there's something that's not quite right there and that we don't really understand. But so the message for this presentation is that these two objects that lie very close to this limit where there was no companions are in fact very young objects. So it tells us something about the mechanisms that are at stake there. Okay, so another set of observations is linked to what's called the Rossiter-McLaughlin effect. This is an effect that occurs when you have a companion that's transiting in front of the star. The star is rotating, so one of its sides has spectral lines that are shifted towards the blue. So the side that is going towards us, the side that's going away from us is reddened. And so when a planet crosses the star, if the spin period if the spin is large enough, you can get a detectable signal on the radial velocity of the system that looks like that. So it's nicely symmetrical if the plane of the orbit is perpendicular to the spin axis of the star. On the other hand, if the plane of the orbit projected along the line of sight is tilted, so it means the star has some obliquity compared to the orbital plane, then the signal is not symmetrical anymore. So we can really detect the alignment of the orbit. It's a very powerful method. At the beginning, like 5-6 years ago, all the objects that had been looked at with this method were in the first situation. So the orbital plane was perpendicular to the axis of rotation of the star, as you'd expect for planets that are formed in a disk, in this standard scenario from Lagrange and Kant and others. So it's actually in the past few years, it's been shown that it's not really the case. So there are some objects that are indeed aligned. We really have the spin axis of the star perpendicular to the orbital plane, but then there's a whole bunch that's clearly not, and even some are retrograde. And it seems that this is linked to the effective temperature of the star that you're looking at. So that the objects that orbit around stars that are hotter, more massive, seems to be more misaligned generally, and those that orbit stars that look more like the sun seems to be more aligned on average. There's also another study by Amoy Trio from the Geneva team that shows that there's also a correlation with ages. So it seems that the young systems are more misaligned than the old systems on average. So as if there's something that realigned the systems that some of them at least were initially completely misaligned, probably due to scattering events or maybe quasi mechanisms, and then they get misaligned. One interpretation is that these objects get aligned more quickly because they have a bigger outer convective zone where presumably you could do the dissipation of tidal energy and realign the stellar spin, whereas it would not be the case for those ones. We'll come back to that. So what I'm going to talk about is, I'm coming back to this diagram, is discussing a conjecture that these objects here that we don't see and should be in this area have been swallowed by the star due to tidal interactions. Okay, so what are tidal interactions? Well, the idea is that when you have objects that are very close to a central object that's massive enough, then they exert tides onto the central object. So depending on the mass of the companion, you'll have a tide that will be exerted on the central object that will create this bulge here. So it's a density perturbation. And because there is dissipation that will be going on, I mean, the companion is forcing elements, fluid elements, to move in the central object, so they will not do that instantaneously. There's a lag that's created between the bulge and the axis pointing to the companion, and this lag will act back on the companion so that it leads to secular evolutions. So it's creating a torque on the companion that allows exchange of angular momentum, and it has different effects, as we will see. The magnitude of this effect is related to a parameter that's difficult to to estimate, but basically that's defined this way. So it's the tidal Q, which is the ratio of the maximum energy stored in the tidal distortion to the energy lost during one orbit. So when Q is high, it means there's very little dissipation. When Q is low, there's a lot of dissipation. For the Earth and the Earth-Moon system, we're talking about tidal Qs that are of the order of 30. And that's why the Moon is always showing the same face to the Earth. For the stars and the giant planets, we're generally thinking of values of Q that are from 10 to the 5 all the way to 10 to the 10. So there's a huge uncertainty on the amount of dissipation that can be going on in these objects. And there are lots of things you have to care about when you do that carefully. The tidal frequencies, etc., etc. So basically, we're hiding a lot of physics inside this parameter. The consequences of the tidal interactions are several things. There's, of course, the synchronization of the spin. So that's happened for the Moon. So the Moon's spin is synchronized with its orbit, and it's something that occurs generally relatively quickly, at least for the companion. Then there's the alignment of the spin axis. So as I was showing with the Rossiter-McLaughlin effect, you will tend to realign the spin axis of the star and the spin axis of the orbit. any eccentricity tends generally to be damped. Not always the case, but in general it's the case, because when you come close, you will, on an eccentric orbit, you will undergo strong tides, and that will tend to circularize the orbit. And then, because generally the central object is not synchronized, you tend to exchange angular momentum so that if you're orbiting, spinning faster here than the orbit, you will give angular momentum to the companion, so the companion will be pushed out. So it's the case of the moon with the Earth. The moon is slowly going out. If it's the contrary, and it's the case in most of these extrasolar systems with close-in companions, the star have spin periods of 10 days or so, while the companions that we care about have orbital periods of several days. Generally, you're pushed inwards. So it's a problem for, of safety for these companions, because the closer they go, the larger the tide, and it's really, once they get in, this will happen very rapidly. So the timescales for all these is linked to the value of this tidal dissipation, but also it's linked to the orbital separation in units of the radius of the central objects to a very high power. Here it's a to the power minus 13.5. So as you go, if you're very close, you can have tides that become important. And then if you divide by 2 the orbital distance, you can see that the time scale will decrease by 2 to the power 7.5 or so. So it will be something that will be very fast and very dramatic. So unfortunately, the tidal queues of stars is not well known. We know from solar type binaries that we need values of 10 to the 5 to 10 to the 6. It seems like a lot, so not very efficient dissipation. But so far, there's no theory that's been able to explain these kind of values in a way that everybody can agree with that. So really, generally, we underpredict tidal dissipation rate. So with the star-planet systems, we have a new population for which we can really constrain these values, and in a different regime. Instead of having 2 stars, we have 1 star with a much less massive companion. So it's really a different regime, and it's interesting. So people have been studying that. I'm citing there a few studies, but generally they've either studied one system or looked, in that case, at the ages of the stars. So generally, it's hard to determine the age of a star on the main sequence, so there are larger bars. So it means that the value of tidal Q is difficult to get. But in this study by Jackson et al., they're inferring that because you see in this plot the orbital distance as a function of age has a slope, an inner side that's a little bit tilted, that a tidal Q in the star should be of the order of 10 to the 7, so meaning that the objects that were there disappeared and fell into the star. But those studies were just assuming quite a simple parameterization of the problem and not including the spin of the star. So what I will present is something a little bit more ambitious that accounts for all effects that we could model, mainly all the interactions between the stellar spin and the perturbation by the companion, the magnetic braking of the star, and accounting for stellar evolution. So basically we solve this set of equations that look complicated, but in fact it's not. Those are expansions of the eccentricity. It's not intrinsically a very difficult system to deal with. You have the total orbital angular momentum of the system, the eccentricity of the orbit, the spin period or spin frequency of the star and of the planet, but it's not a very important factor. All these are calculated. We're using stellar evolution models to account for how the star evolve in time, and we include magnetic braking. Sorry for the small mistake. We fix the radius of the companion. That's a simplification, but that should be okay given what we know of the exoplanet population that is in transit. So then what we do is that we base initial conditions on the observed present-day population and look to see whether we get something that's self-consistent after some evolution and reshuffling of the ages, as you will see. One simple way to do that is just to assume a fixed Q in the star, say 10 to the 6, and then the orbital migration timescale can be calculated with, it's of the order of, well, it's given by this simple relation. So it's around 12 million years for an object which has a one-day period orbit, which is Jupiter mass and orbiting a solar-type star with solar mass, and Q in the star is 10 to the 6. If we use that for all the objects that have been discovered and that were in the previous slide, we get this kind of result. So this diagram is important. There are two things to notice. One is that you get very low values of this migration timescale, less than 10 to the 6 years. So less than 1 million years. So it would mean that we were very lucky if tidal Q is indeed 10 to the 6, we're very lucky to have found these objects. And this is not very reasonable given the amount of objects that we know. The other thing is that there is this trend here, and you see as a function of effective temperature that the objects orbiting F dwarfs, the hot stars, tend to have a much smaller migration timescale. So there is something going on there. What is it? Well, we would expect just from this diagram that the tidal Q associated with F dwarfs should be smaller than that with G dwarfs. But then we have to be a little bit careful because stellar rotation gets in there and plays a role also. So, okay, maybe I haven't been very clear about that. So it's really as the companion is exerting a tidal bulge on the star, if the star is spinning slower than the orbit of the companion, which generally is the case, then it will tend to drag the companion inward with this time scale. So this is the ratio of the orbital distance to the A dot, so the derivative of the orbital distance with time, and because of the way it scales, there's this factor in front. Okay. So something that we have to consider is stellar evolution. And I've been talking about effective temperature. this is a diagram showing how the effective temperature of a star evolves with time as a function of metallicity. And you can see that it's very dependent on the metallicity, with low metallicity stars in blue having higher effective temperatures for a given mass than high metallicity stars here in red. And this is something that has to be taken into account in the models. And this is something that we're doing. So at what's happening there is that after the star, after several billion years, the stars have evolved on the red giant branch and leave the main sequence, and they will become white dwarfs. So they disappear. And the more massive the star, the faster the evolution. So that's what's happening. Yes?
How do you get a negative ratio of iron to hydrogen?
Okay, I didn't talk about that, but this Fe over H is it's a log quantity. That it's a log of the ratio of the abundance of iron to hydrogen in the star divided by that in the sun. So it's 0 means solar, minus 0.3 means half solar, and plus 0.3 means twice solar. As a standard way of doing that in astronomy. Thanks for the question. Something we also have to take account is magnetic braking. So what I will just try to really well, show very briefly what's happening there. Basically, you have loss of angular momentum in stars due to mass loss and magnetic field breaking. So what happens is that this is something that's been discovered by Avery Schatzman in the 60s. When you have a star, it's losing mass up, and you have approximately solid rotation up to what's called the Alfvén radius. And so from this Alfvén radius, you will lose angular momentum at a rate which is governed by the mass loss times r square omega. And there's this factor that depends on the geometry of the magnetic field. There's quite complicated physics hidden in there, where this is the Alfvén radius. So further from the star, at several stellar radii, you have a wind that's not in solid body rotation anymore, and the interaction of the magnetic field of the star with this wind is creating the loss of angular momentum. So to actually calculate how much you will lose angular momentum, you have to assume that the Alfvén speed is equal to the wind speed at this Alfvén radius that depends on the magnetic field strength. So that allows you to link RA and B. You have to assume that there's isotropic mass loss, so that the mass loss is proportional to rho, the density, V, the wind speed, and RA square. We have to assume something about the radial magnetic field that decays generally with 1 over R square. And you have to use an empirical dynamo relation that links the strength of the magnetic field at the star surface to the spin period of the star and its radius. And generally it's been observed that you get this kind of quantity, so that if you have a big star with a large radius, it will tend to have a smaller magnetic field. And because of that, when you use all these relations, you can calculate a breaking timescale which is proportional. So it's the angular momentum divided by the derivative of the angular momentum with time, and it's proportional to the moment of inertia in dimensionless units square times the mass of the star to the 3/2 times the radius of the star to the 3/2 times the spin frequency to power -2. So what happens is that the faster you spin, the faster you break. This is what's in there. And then the more massive or the bigger your object, the slower you break. So F stars will, because of this relation, will tend to break much more slowly than G dwarfs. And so when you include that in the model, you get a very nice agreement with some completely independent studies in a different regime between observations and the models. So the blue dots are the observed population, the red dots are the simulated population started with an arbitrary high velocity initially, and rapidly they spin down to get something that's very close to the observation. So that's quite nice. If
estimate as well?
Actually, that's done. Thanks for the question. It's assuming no age estimate. It's just randomizing the ages between the 0, basically, and the age, the maximum age on the main sequence of the star. Okay, so we have enough stars, so we don't have to rely on ages. That's the nice thing of this approach. So if we instead adopt a breaking relation that's independent of the stellar parameters, as is done in some studies, then you get something that's completely discrepant with the observations. Okay, so now let's look. I'm going to show some movies here. So this is orbital period as a function of effective temperature for observed object. I'm going to restart from the beginning. So those are observations. So you have color is linked to the metallicity and size of the dots to the mass of the companion. So those are to the bottom companions that are very close to their star, so they may be swallowed, and others up there are safer. So those are the observations. So we, in red, I will appear the initial model. Okay, so that's what we put in the simulation. It's just it mirrors the observations, just to see what's happening for this population. And then you're going to see that all these companions rain down, they're being swallowed by their star. But this is a model where we assume the fixed stellar Q to 10 to the 6. And then stellar evolution moves the objects that way. So you're losing with time, this is age, you're losing these objects, but just because the star disappear. And then in order to compare with the observations, you reshuffle the ages so that you have something consistent with the observations. And here on this diagram, it's difficult to see whether we're doing a good job or not. So it's actually much better to consider the migration timescale that I showed earlier. And there we will see that there is clearly a problem. So again, we have the theoretical models. And you can see that all these objects are lost, as you would expect, very rapidly. So they disappear. Then we will reshuffle the ages to get a nice comparison with observed constraints. And you can see that only the objects up to that line, several 10 to the 7, have been left in the simulation. So clearly we have a strong disagreement with this model. Okay, so there's been a proposal for the dissipation in the star due to waves created in the star. So there's I don't have time to go into any detail there, but basically a number of things have been shown to be too weak to create efficient dissipation, in particular equilibrium tides. But the recent proposal that I'm going to concentrate on is a dissipation of gravity waves in the stars. So the idea is that when you have a star like the Sun, it has an outer convective zone and an inner radiative zone. In the radiative zone, you can create gravity waves. So gravity is the restoring force. And the waves are launched at the radiative convective transition. And you have a wave that propagates. And at the center, because of the properties of the center, you may have dissipation. And in that case, if you're able to dissipate that energy, you will have a tidal Q that may be low enough to explain some of the observations. So the idea is like on the sea, when you have a wave, sometimes when it gets large enough and close to the shore, it will break, and there you're dissipating the energy that's in the wave. So, well, you can surf on it. It's more difficult on stars. And then you can see that because of waves, you can get a lot of dissipation and actually create some messy things. So that's in Nice. That was this year, but I was not there. There was a big storm on the Promenade des Anglais. So waves are important for dissipation. So in that model, the idea is that because of the way the physics of the stars work, these waves tend to amplify near the center. So they're governed by this equation. And if they're amplified enough, so then they can become nonlinear, and then you will dissipate this energy. So either that the displacement becomes larger than the size of than the radius itself, as in this diagram, or actually you can have dissipation because the entropy profile becomes tilted so that you can generate convection in there. So that gives you a slightly less stringent criterion. So this is work that's been done recently by Barker and Ogilvy. What they showed is that it depends on the mass of the companion. So if you have a big companion, the amplitude of the wave will be bigger, and so you will be able to dissipate. And in that case, you can get tidal Q factors that are of the order of 10 to the 5 for a one-day orbital period object. Okay? But for that, you need to have a radiative center, otherwise it doesn't work. So you have to really look at the structure of the stars very carefully. So this is the evolution of stellar radius with time as a function of mass. We're still in the pre-main sequence there, some tens of million years. And here, this is the convective zone, external convective zone, internal convective zone. What's happening is that for stars that are 1.2 solar masses or more, they have an internal convective zone. So this route for dissipation is not possible for them on the main sequence, whereas you can dissipate for quite a long time around solar-type stars. So this is what we're doing in the model. Whoops, sorry. Where am I? Okay. So in that case, using this model, we're dissipating more in solar-type stars than in F-dwarfs, and you will see that on average you get something that's much closer to the observations. We have to wait a little bit till the evolution is done, and you can see that it compares much better than in the previous case. Okay, so this is the same diagram. So this is mass and effective temperature as before. So I've put initially a lot of objects in there, and you will see that they will dissipate. They become bigger because size is linked to the orbital period. Okay, the star evolution that way, but basically you've lost these objects, so you've really created a void of objects in there. And that's due both to the, actually, to the dissipation in the star, but also to the fact that the stars, the F stars, are still rotating fast and are not able to extract a lot of angular momentum in these systems. So basically, we have this kind of plot that's for a fixed initial 3-day orbital period, looking at lots of systems. Those are the observations. And I'm looking at the contours, and the colors here are the lifetimes, actually, in terms of the maximum age of these systems. So this is 10% or less, 20% or less. So basically, you're losing these close-in massive companions around these stars. You're not losing those, although there's efficient dissipation. This is because there's a lot of angular momentum in the orbit of these massive companions. So it takes time to extract this angular momentum. So you don't expect to lose those very rapidly. Then here, you don't lose these companions because tidal dissipation is less effective in these stars, and also because they extract less angular momentum. And then the low mass companions are below the critical limit generally, although this is time dependent, and at all ages there are interesting things to look at. But in these simulations, they're conserved, so they're safe. Okay, I'm going to skip this animation. This was the velocity of the star to show that the stars get spun up by their companions. I'm going to just briefly show a little bit of some preliminary statistical tests that I did using a method that's called the probit method. It's taken from econometric, and the idea is that you create your list of objects, you add a column of an observed column that is 1 for the observed object, that is 0 for the theoretical objects from the model, and you correlate each quantity, period, eccentricity, mass, whatever, with this column, this observed column. And if the two models are identical, there should be no correlation between any of these quantity and this observed column. That's the essence of the idea. So you can get, so those are the parameters. So you get results that are like this. So different models, you test different values of the stellar Q. You look at some parameters. So this is the migration timescale, the mass of the companion, the mass of the star, metallicity, effective temperature. And the important thing is the probability that the model and the observations agree. So this should be as close to 1 as possible to have a good model. So for this model where we don't account for the spin-up of the star, which is often done in some studies, we have a very bad match. Nothing works as expected, actually. When you have a constant Q, we actually find models that work. Those are models with very low values of the dissipation, around 10 to the 9. So that would be compatible with the models. But it would mean that the correlation is due to chance. There's still some work. The correlation between migration timescale and effective temperature would be due to chance. So there's still work to be done on that. So the last model that works best is the one with internal gravity waves, and we're parameterizing the dissipation when there's a convective interior, or when we're below the critical mass, for example. And this works for a variety of cases, and so you're getting values of the probability that are quite reasonable, of the order of 0.2 or 3 or 4. So I will finish with that. So by saying that brown dwarfs and massive planets that formed as close companions to G dwarfs have been engulfed by their parent star. That's what this study shows. And that this naturally explains this part of the brown dwarf desert, so which concerns the close-in companions. And this is due both to the high tidal dissipation in G dwarfs and to the larger magnetic braking that they undergo. And probably our two planets that I talk about, Coro 2b and Coro 18b, are young and they're on their way to engulfment. And this method provides a way to constrain tidal Q to more than 10 to the 7 in F dwarfs and around 10 to the 5 in G dwarfs for companions of around 3 Jupiter masses, with agreement between theoretical and observed populations. We observed that stars are spun up by their companions. There's still work to be done on that, so it's still ongoing. So in particular, we want to include the evolution of the properties of the central regions of the star that affect the critical mass at which you have this dissipation. And this is something I'm working on just right now. So stay tuned. And thanks for your attention.
Tristan, can I kick off the questions? I was wondering, is it possible to track stars that have had the migration of brown dwarfs into them by metallicity? Is this a proposed method that we can track where migrations have occurred?
Yes, I mean, there's this possibility. If you engulf a brown dwarf, then generally you will have more lithium than you'd expect for a star of the same age. Then it's a matter of what is its outer convective zone mass compared to the mass of the brown dwarf or massive planet that it has engulfed. And we know that there's some variability in the lithium abundance, so maybe that could explain part of that. It's not clear really how you can study these, because of course the companion is not there anymore. So, but yeah, it's a possibility. And tying to the evolution models, it's interesting because some stars have smaller outer convective zones. So if we have a lot of them, we ought to be able to test statistically for that.
So the brown dwarf desert for solar-type stars seems to extend out to several AU. And can you explain that whole?
Yes. Yeah, thanks for the question. I was actually talking only of the close-in brown dwarf desert, as you know, and I can't say anything, of course, of the objects that are further away and from their star, because they don't undergo tidal interactions, and this has to be due to formation.
Hi, I have a speculative question.
Yes.
Even allowing for observational bias of extrasolar systems so far, it seems like our solar system is kind of the odd man out, with the innermost planet having like an 88-day orbit. And so I was wondering if possibly we might have had a Jovian really close to our sun at some point in our evolution that got swallowed up.
Well, it's very difficult to answer that question. People don't think that way, that it's the case, because it would have created havoc in the inner solar system. And it seems that in order to form the terrestrial planets as we know them, you have to have something relatively quiet. So it seems it hasn't been the case for the Sun. But it's true that when we discovered exoplanets, and a lot of them were close in, we wondered, well, why in our solar system do we have the giant planets further out? Now we're discovering systems in which the giant planets are further out, and so there are various ways of doing that. For example, with interactions between the giant planets themselves, you can stop the migration. And now we're discovering these small super-Earths that are very close in as well with the Kepler results, and so it's a problem. Why it doesn't have the solar system some terrestrial planets inside Mercury's orbits? We don't know. And so I think the Sun cannot have swallowed a giant planet, but I would not bet my hand on that. So.
Is there an observational or even theoretical bias towards systems in which swallow their companions versus systems like the Earth-Moon system where the companion actually migrates outwards? And is there I didn't see that there was an establishment of a dividing line between systems that engulf their companions versus systems in which the companion migrates outwards.
Yeah, so of course there is, I mean, if you consider companions that have orbital periods of tens of days, then the tidal interactions push them outward, but so slowly that you don't have to take care about that. There are some systems in which the star is rotating faster than the planet, and yet the planet is very close in. There's one which is Coro 11, which is very interesting. So the star, it's an F star, so a massive star, and it's rotating in less than 2 days, I believe, and the planet is a little bit further away. And it's hard to explain how this one was formed. Actually, one of the reference that I had in there was studying this particular system. Is there a bias for one against the other? I don't think so. I think it's just there's a bias in the sense that the stars break quite quickly, especially when they're fast rotators. So it's very hard to find stars that rotate quickly enough to be spinning faster than their close-in companion. So generally we will consider inward migration mostly.
How fast is our sun rotating?
Oh, yeah, that's a good question. I didn't mention that. It's 24 to 29 days. It depends on whether you're looking at the equator or at the poles. But yeah, it's a pretty common star. So for 5 billion years and that effective temperature, that's the kind of spin period that you get.
Okay, well, if there's any more questions, I encourage you to come and speak to Tristan after this. Tristan, we have a special Are We Alone mug. Hopefully you can use it to store extra brown dwarfs or something like that. So please join me in thanking Tristan for his great talk.